wage of men with education level 5, okay, is larger than the mean hourly wage of women with education level 5 of the same age. Okay, so we need to include age, we already know that. Then we answer this using data set XMP 2111, and the following model. And like I said, if you have to do quite a difficult model, then often you get the model. You have to create the terms yourself, but at least you get the model. So here we have D1, D2, D3, D4, which means that D5 is the base level, because you always leave one out and you get dummy 1, dummy 2, dummy 3, dummy 4. So D5 has to be the base. Yeah, they already say that here as well. And we are going to have to make this model ourselves. So we go to Canvas. You download XMP 2111.sav. And here is our model with the wage, the fem, dummy, and education level. And which ones do we want to make? This is quite complicated because age we have fem, D1, D2, D3, D4, we don't have yet. So first we are going to make those. Remember how we did that? We go to transform, compute variable. And we still have this, so you can just correct it. And this is the old model. I have to close this up and go to the new one. Transform, compute variable. And then we want D1, we call it D1, if the education level is equal to 1. You click on OK, and you are going to do that for the first full. So this is to be 2. Okay, do it again. 3. 3. And one more time, 4 and 4. Okay, so now we have at least our dummy variables. You can see them here. But we had to make a few other terms as well, because we have to interact the fem with D1, the fem with D2, fem with D3, and fem with D4. How are we going to do that? We don't have them yet, as you can see. So we have to make them again. You go to compute variable again. You say fem D1. You're going to interact your fem with your D1. It's actually as simple as that. It's just a bit of work. You click OK. And you're going to do that for your other variables as well. Then D2 times D2. You can just change the numbers as well. For the third one, and for your fourth one. And now if we look at our data, this is now our data. Fem D1 is 0, 0, 0. And when is it going to be 1? If you have a female and an education level of 1. So is it ever going to, yeah, here it's 1. So we should have a female. Yes, we do. And we have education level 1. So they're both 1, and you get 1. Fem D2, should be 1 if you have a female and education level of 2. So here femd21 is 1, and you go and look, and you have a female because it's 1, and you have an education level of 2. Thus you have femd2, so this returns 1. Why doesn't it return 2? Because 1 times 2, you'd say it's 2, right? It isn't the, how do I say it? It's not, it's like you don't multiply it. It just returns 1 if it has those values. All right, so because D2 is a dummy variable, so it is 1 if education level is 2. And fem is 1 if it's a female. So if they both are 1, then you have 1. Yeah, that would be the explanation. So now you have all those, and you want to make a model with the age, the female, all 4 dummies, excluding the base level, and the interactions. So you go analyze. Oh, 1 second, it's running low on power. Okay. So you want to make the model, and you go to Analyze, Regression, and Linear. You put in your wage on the dependent variable. You put on your fem. If you put on your finger on the control button, then you can take all of them together. And you want all of them, so that's easy. And you put them in there. You click on OK. And you get this model with fem, education level, D2, D3. I think I forgot age, right? Is age even in this output? Yeah, it is. Sorry, I forgot age. We have to do it again. Regression, linear, and you're going to put in age as well. You still had everything from the previous. Only now notice that my age is going to be on the bottom. I might be able to move it. I don't. No, I'm not. Maybe. No, it still gets at the bottom. So, like I said, you have to take notice of where your variables are in the model and in the actual model, so you don't get confused with the betas. But I said usually you should put it the same, but if I have to put it exactly like that, then I have to go to make it again, and I don't want to. So yeah, my age is going to be at the bottom. And what do we want to test? We want to test if the mean hourly wage of men with education level 5 is larger than the mean hourly wage of women with education level 5. Okay, so education level 5. Then all the other dummies are going to be 0. So this one is 0, this one, and in fact, all these are going to be 0 because they all have other dummies, and none of them is education level 5. So we want education level 5, all others are 0, and anything times 0 will be 0. So from here until and up including here, this is all going to be 0. So the only terms that we have is beta 0, beta 1 age, they have the same age, so that will be the same for both, and beta 2 fem. And beta 2 fem will change because the wage of men and the wage of women. And of course, fem returns 1 for a woman, and it returns 0 for a man. So if the fem is 1, then you get this, because you do B2 times 1 is B2. But if it's a man or a male, this is going to return of course, 0. So it falls away. The only difference between the two is beta 2. And what did we want to test? We have a female dummy and going from so men have higher wage, and going from a woman to a man thus needs to return a negative number. Thus we test whether beta 2 is less than 0. Because again, there is no value given, so we take 0. If you do that, you go and test it. This is your hypothesis. We want to test just one variable in the model, so we are going to take a t-test. And the t-statistic is the big T, of course. Your B, in this case B2, as you can see here. This is the beta, but we always take the B because you are testing a sample model, so you have to take the sample terms. So B2 minus the hinge, which is 0. You can also, by the way, write B2 over SB2, because the 0 you can disinclude. If it's non-zero, so 3 or something, you have to include it. But if it's 0, you can just write it like this, leave the 0 out. But you can also write it like this, which I personally think is nicer. And then the value of the test statistic is this. So we have the B2, fem education level. For the fem, it was for fem. Remember, my model is a bit fucked up, so yeah. But we were looking at fem. And if you take the t, you can take it from the graph because we have a hinge of 0. And this is going to be your t value. What is your critical value? You can do it in Excel, but we've done it quite a few times. So yeah, let's say that it's this. I'm not going to calculate it because we've done it very often already, and it's going to take too much time. So this is our critical value. And of course, this one is smaller than this. Thus, if it's smaller, it's so surprising that we can reject H0. If we reject H0, then we tentatively accept H1, which means that the hourly wage of men with education level 5, and I would say the data suggests, or the evidence suggests, that the mean hourly wage of men with education level 5 is larger than the mean hourly wage of women, keeping age and education, keeping age constant and having education level 5, something like that. As long as you include all terms, so say the same age and education level 5 and make the correct conclusion. The last chapter, chapter 22, is about testing model assumptions formally. We had four assumptions: the linearity assumption, homoscedasticity, independence, and normality. And we made graphs to test them. And that's one way to do it. But if it asks formally, you always do a hypothesis test. I wrote that down here in red. And if it says formally, you do a hypothesis test. Sometimes it says using the p-value method or a critical value. And then, of course, you also know that you need to do a formal hypothesis test, because, of course, you cannot read a p-value from a graph. But if it doesn't say it, you probably can make a plot or a histogram, like we did before. And so there is one thing. We discussed collinearity. Remember that there's collinearity when two of the independent variables are strongly correlated, and if there's perfect, they are like in a linear relationship. And this doesn't reduce the explanatory power of the model, but it does make interpretation of the coefficients more difficult. Why does it make it more difficult? Because you don't know whether, for example, remember we had this model of household size and kids and expenditure on clothes, and you don't know if your clothes expenditure goes up, it's due to household size increase or due to the number of kids increase. So that makes it a bit difficult to interpret the variables or the coefficients of the variables. And moreover, it increases the size of the coefficients, standard errors. And that's also not so nice, because if you have your prediction intervals will get bigger, your confidence intervals get bigger, and your p-values also get bigger. And like I said, you don't need to know why, you need to know that it happens. What could you do? You could remove the offending variable. So for example, remove a number of kids. But you probably don't want that, because you want the information on the children. And sometimes you can create a new variable to remove the problem. In the household example, the household size and the number of children, you can create a new variable, which is the number of adults. So that's the household size minus the number of kids, of course. And then you can use the number of kids and number of adults, which are not linearly related. Because if there are more adults, it might not be that there are less kids, because, for example, a new partner comes or something. And then like if there's a mother alone with 3 children and she gets a new partner, then there comes one more adult, but there's still the same number of children. And so those are not linearly related. And then you include the number of kids and the number of adults instead of household size and number of kids, which usually are linearly related, as I already explained. But usually you don't get such questions. It's really just for your own understanding. But the other assumptions, so nonlinearity, homoscedasticity, independence, and normality, are very important to know and to test. So we are going to learn that now. We will start with nonlinearity. Remember, the original model had the assumption of linearity, which was this one. And linearity said that at every point on the graph of x, the error term should be 0. And why is it 0? Because the expected value of y is the line, of course. So the error term, the expected error term is 0. So if you take the expected y given x's, this is your expected value of y, excluding the error term, because you expect it to be 0. In reality, it's probably never 0, as we know. But yeah, we expect it to be 0 if we look at the line, of course. And what you do is there are 4 steps for linearity. You estimate the original model. And since you want to see if it's linear, you need to test if there is a possibility for non-linearity. So, for example, does it depend on a nonlinear term? So what you do is you estimate the original model and you save the predicted values. And then you create a new variable, which is the square of the predicted values. So y hat squared. And you estimate the auxiliary model. So this model plus this term. And why do you add this term? Because it's a quadratic term. And if y depends on a quadratic term, which is a nonlinear form, as we discussed, then it's nonlinear. Then y isn't linear. And then you can, of course, prove non-linearity. So what you do is you want this coefficient before the y hat squared to be 0, because then it doesn't depend on it and it's linear. But if it's non-zero statistically significant, then it does depend upon it. And it's non-linear. So if you want to test just one term, you apply a t-test. And you want to see if this is 0 or if it's non-zero. Okay, and if it's non-zero, then it does depend on it, and then it's non-linear. We're going to do an example, and we will open the baseball data set, which is in week 6, if I recall well. Sorry. That was me sneezing. Okay, we're going to open this one. And you close the other ones. So here's our data set. This is a rather difficult one, I think, because I'm not familiar with baseball. So I don't really know what it stands for, but anyways, it says Y is the number of runs, or X1 is on base percentage, OBP, and X2 is slugging percentage, SLG. I have no idea what those are. But anyway, we want to test this model. So whether the number of runs depends on the OBP and SLG. First, we are going to make this model. Go to Analyze, Regression, and of course Linear. You're going to put the runs in the dependent, and we wanted to test if it depended on OBP, SLG. You're going to tick on Save, and you're going to tick the unstandardized predicted values, and also take the unstandardized residuals because we might need them later, but we don't need them now yet. You continue and you click on OK. And if you okay, I don't know if it's okay, it's not working, as you guys see. I don't know why, I didn't have this before, but there's something wrong with our data, it says. So I don't think we try again, but like if there's something wrong with the data, then it's not our fault. Okay, it's deleted everything, that's nice. Okay, I think we can't use it, I'm sorry. We only need it for one example, so it's not like we're gonna die. But fortunately, I have the how-to made on here. So what we would do is you analyze and regression, and you go to linear, like we did, and you make the model. And then you save the predicted values, like we also did. And like I said here, you have to square the predicted values. So how would you do that? You would, I can show it to you. You go to transform again, and you do the compute variable. And then here should be your predicted values. If the data was correct. I don't know what's wrong, but it's not our fault. So I can't change it either. And if you had your predicted values here, you put it in here, and you just do it squared. Remember, like you took it, and then you put an asterisk in between, and you put it there again, and it squares itself. And you call it something like predicted value SQ for squared. And then you are going to take your model again. So you go to regression, linear, And if we had our data or our variables, then you would have still the same model as I showed you here. You have the same model, but you add your predicted value. And this weird sort of y, that thing, is just to show you that you could put a b in front of or a beta in front of it as well. It doesn't really matter as long as you know that this is your coefficient for your predicted value. But it could be a beta as well. They use this weird y here. And then you get your output if everything goes well. And then you want to test if that coefficient, so this one, if it is 0 or not 0. And yeah, here I included the output, which you should get if there was nothing wrong with the data. And so you get your predicted 2. Here they call it pred2. I always call it pred squared or SQ. Here they call it pred2. So what's your coefficient? Oh, it's already, you see that it's 0.000. So that's very, very small. And if it does have influence, it only has small influence. But let's see if it does. Here you see that your t value is this. And your significance is very small. So if you take, for example, alpha is 0.05, then you may reject H0. Why may you reject H0? Because it is your significance level is smaller than your alpha level. So under the null hypothesis, it's very unlikely. So you reject H0, and if you reject H0, so you reject this, you accept this one. And if you accept this one, what you're actually saying is that your coefficient is not 0. So it does have influence. And if it does have influence, then your y depends on a quadratic term. If it depends on a quadratic term, because this is non-zero statistically, then it's not linear. And like I said, it only is a very small coefficient. So probably it's close to linear, but this is statistically significant. So it's, if you would click on this, you would see that it's actually 0.001. Here it's rounded off a bit. So it's not 0. It's very close to 0, but it's not 0, and it's statistically significant. Thus, the y is non-zero, and we reject H0. We thus accept H1, and this is a term that describes the model well, and it adds to the model. And thus, y depends on a nonlinear term, meaning that there's a violation of linearity, or you could say that we have non-linearity. That's the same. They say it here, there's evidence of non-linearity, concluding that the standard errors are not reliable. If there are any questions, you can ask. I'm sorry that I can't show you. I don't know what's wrong with data. But I assume, I've never had this before, by the way, so I assume everything should be right in your test. Yeah, I don't know what's wrong, but we'll just leave it. Oh, no, I don't want to save it. Because we have another document for the following examples anyway, so we don't need it. Then we're going to test the second one, homoscedasticity. Remember, homoscedasticity meant that there is a constant variance of your error terms, which said this. So your error terms, the variance is always this, so it's constant. And heteroscedasticity is when homoscedasticity is not true. So homo is the same, hetero is different or opposite. And so when you have hetero, you don't have homo. And so that's when the variance of E varies with the X variables. Thus, it's not constant, as homoscedasticity suggests. And in the presence of heteroscedasticity, the standard errors, again, may not be reliable. How do we test it? We can test it formally in SPSS. So we are going to look at the steps again. Again, you estimate the original model. This is our original model. And you save the residuals. Why would you save the residuals? Because you want to see if Y depends on them. If Y depends on the, if you want to see if the residuals depend on the X values. If the residuals depend on the X values, then there might be, for example, very big ones at big values of X and very small ones at small values of X. And if that happens, of course, then the variance is not constant. So you create a new variable, which is the square of the residuals. Why would you square them, you may ask? We've seen them, we usually square them also in your SSE. If you recall, you do because otherwise they cancel out. Because of the linearity assumption, they have to be in equal parts above and below your regression line. That's the principle of your regression line. And so they cancel out. And if you square them, then the negative values also become positive, and then they don't cancel out. So then you can test if at small values the E squared is, for example, very small, and if at bigger values of X is very big, then of course, then there is no constant variance. And that's what you want to test. So you want to test if E squared depends on your X's. What you do is you are going to test if your E squared depends on those. So you fill in your normal model, but instead of your Y, you fill in E squared as your dependent variable, because you want to see if this depends on your X's. And you're going to, again, apply the F-test to see if those are non-zero, those coefficients, or at least one of them is non-zero, then of course E squared depends on at least one of those. And that's a violation of homoscedasticity. If those are all statistically zero, then it doesn't depend on the X's, and you have homoscedasticity. So for each X, the E squared would be the same. But if it's not, then it will depend on the X's. Those are non-zero, and you will have heteroscedasticity. If there are any questions, just interrupt. That's okay. So, yeah, we need a baseball example again. Shit, I thought we didn't, but we do. Let me try to open it again. Maybe it will work. Okay, here it is. And otherwise, we will just try it with another data set. That's also possible because you can do this test, of course, with any data set. Okay, so what are we going to do? We are going to test. We first always have to estimate our normal model, regression and linear. So we put in the R on the dependent variable, and we put on the OP and the SLG here. And we save our unstandardized residuals. Now it works. I don't know why it didn't work. Maybe we should have tried again, but at least it works now, so I can show you this one. Okay, so we have our normal model, and we have our residuals. Here are our residuals. But like I said, you have to square them, because otherwise they cancel out. So I call it res rest squared or something, you put in on your unstandardized residuals, you multiply it with itself, or you can also do it this double asterisk. It also works. Oh, it doesn't work well. Okay, then we do it the other way. This happens quite often to me as well, by the way, that something doesn't work and you just have to try it another way. I hope, yeah, this works. Sometimes there's no real good explanation. Sometimes you put like a space between it and then it doesn't work, or those things happen. Okay, here's our residual squared. Here you see they're all positive numbers. Here it's a -1. And if you take them all together, they should become 0. And that's why you cannot take the normal residual term. And I square them. So now I've squared them. And what we're going to do is the following. We are going to regression again. We're going to a linear. We only use linear. And we don't want the R here. We want our residuals square here. Because we want to see if our residual squares depend upon this. You click OK, and you get an output. And what are we going to do? We are going to do an f-test, because we want to see if any of these variables or variables is, if any of them is non-zero. So we do an f-test, and our f-statistic and our significance, this is 2.434, and our significance is 0.089. Of course, we can get our critical value in SPSS, but using the significance usually is easier if they have given a significance level. So we've done this, and they give us a significance level. That's easy. So they give us an alpha of 0.05. Okay. And what is our significance? Our significance is, or our p-value is 0.01. Is that then bigger or smaller than our 0.05? Of course, it's smaller. So, because it is it smaller? It's bigger. I'm really bad at seeing those numbers. If you ever hear me say like number, for example here, 447, that's because I can't pronounce it. I don't know why. I've had it my entire life. So I'm also really bad at seeing which is smaller here. Sorry for that. But this one is bigger than this one. So if our p-value is bigger than our alpha level, then we cannot reject our H0 because it's not surprising enough under the null hypothesis. And if it's not surprising enough, then we cannot reject H0. What was H0 again? Our H0, I didn't include it here, but our H0 was testing whether these are all 0 versus whether one of them is non-zero. Recall the f-test. So testing them, you say H0 is at least one of them is non-zero. And for H0, you say they're all 0. And I just said you cannot reject H0. If you cannot reject H0, then there is evidence that those coefficients are all 0. And that is good. Why is that good? Because it allows us to conclude that the error terms do not depend upon the axis. Why? Because those are 0. So it doesn't depend on the axis. And if it doesn't depend on the axis, then we conclude that there is homoscedasticity. So that the E squared doesn't depend upon axis, so its variance is equal everywhere, or at least that is what the test says. So there is not heteroscedasticity, there is homoscedasticity. So the standard errors should be reliable. I know this is this can be a bit difficult. So if you have questions or I'm going too fast, you please let me know. So if we have heteroscedasticity, so the error terms depend upon the axis and there is non-constant variance of your error terms, then there is a small solution for it. You can bootstrap, and they'll probably never ask it, but I'll show it to you anyway. So you go to your model and you go to Analyze Regression Linear. And somewhere here, I think no, it's not under Options. Oh, here's Bootstrap. And you click Bootstrapping. And this is all fine, and you just continue. You click on OK. And here you get some Bootstrap specifications and stuff, and it's running a bit weirdly. So here you get your bootstrapping, but truly you never really need to do it. It's it's just a function of SPSS, but I've never seen it being asked in a test or anything. They'll never ask what are the bootstrap coefficients, I would say. But if they do ask it in case, then you have seen it. And then you get your bootstrap for coefficients. And if those are your normal coefficients, then if I make it a bit bigger, then those are your bootstrap coefficients. And as you can see, they're all a bit smaller. Because if you have heteroscedasticity, it overestimates the standard error, like I said. So if you perform bootstrapping, they'll all become a bit smaller. Usually this one becomes bigger, so it's also not necessarily a constant. But anyway, that's not very important. What is important though is that you are able to do those testing things. That will, at least one will come up in the test. If we have normality, there is, like I say here, and in the slides, not that I would make this up, we don't discuss formal testing for normality because it is very complicated. But if they are not normally distributed, the standard errors are not reliable. But we don't, of course, have to test if they are or not, but you just have to know if, for example, they say the normality assumption is violated, what could you do? What could you do is changing the regression specification, and that can sometimes help. For example, you use the ln(y), the natural log of y, instead of y, and that will make outliers smaller. I think we had this in mathematics. So the natural log makes numbers just on a different scale, and they usually become smaller. So large outliers, a very large number becomes relatively smaller to a smaller number. So how would you do that? You can go to your data, go to transform, compute a variable, you take ln, say for example, ln(y) of your ln(y) of r, and then here you put just ln, and then you put your r in it, and you would get an output. But also, I don't expect this to come up in the test. You just need to have seen it so that you won't get angry with me if it does. But like I say, I've never seen it being used. And to be honest, there wasn't put a lot of emphasis on this. It was quickly discussed like a minute. And I think if it really does come up, then it should have been discussed longer. Then there is the last violation. or possible violation. Remember dependence of the error terms. We said we want the error terms to be independent of each other, because if they are not, then the model isn't reliable anymore. Because if they are not independent, then what will happen is that they sort of the data depend upon each other, and your sample, of course, isn't fair. And if we have cross-section data, this is usually not a problem, because we take 100 people from the population, from all states or something, and you hope that they're independent. But if you take time series, then probably today will be related to yesterday, and tomorrow might also be related to today. If you, for example, take the stocks, I don't think stocks are completely independent of the previous day. For example, if Tesla goes up a lot today, then tomorrow, if there are more signs or something, that's probably related, right? It's not that tomorrow is completely loose or independent from today. And what you can do is sometimes you can change the regression specification. So you can use differences instead of levels. You can use growth rates or adding a time trend. These are just suggestions, and you don't really need to know them, because we don't really know what to do if it happens. We only need to know to test for dependence or independence. So if we have dependence, a formal test, again, we have 4 steps. And the first step is always sort of the same. You estimate the original model. And what you want is you want to save the residuals. That's, I think, obvious, because you want to test if the residuals depend on each other. So what you save is the residuals. And there is an example. Then you create, again, a new variable, which is the lag of the residuals. And what does the lag mean? The lag means that it's the day before. So if you have tomorrow and you want to create the lag of tomorrow, you take today. It's the day before it. And why do you want that? Because you want to say, you want to see if tomorrow depends on today. And if you create all the residuals and all their lags, you can see if all the days depend on their previous day. And then you estimate the auxiliary model. In this case, and I think it's good to know those things by heart. It isn't very difficult. You can all rationalize them. But anyway, I just say it because you might think it's not important, but then you're on the test and you think, you just get confused because there are 4 options. And if you just learn them, then you will be able to do this, I think. So you're going to estimate a model. And this model is the following. It says ET, and then this weird Y again, probably has a name, but I never had Latin or Greek, so I don't know. And you have the VT, which is your error term. You can also just write the weird E thing, which also has a name, like the turned around 3, I call it. But because you have different notation here, they say VT, but it stands for your error term. And you have this one, so the ET minus 1. And this is your lagging term. And what it actually says is you are testing if your ET, so if tomorrow, for example, depends on today. So on the day T minus 1, so on the day before it. You could also have T minus 10, for example, and then you test if it depends on the day that's 10 days before it, but usually T minus 1 is enough. And those weird signs are just your coefficients. You could also write the beta again, but they chose to do it like this. If you write the beta, it's probably not wrong. yeah, so it says this weird thing, sort of y1 is the correlation coefficient. So it's your beta effect. And what you're going to do is you want this one to be 0. Because if it's 0, then this term, or the ET, doesn't depend on this lagging residual. If it is non-zero, then it does. So what you're going to do is you are applying a t-test because you want to test just one term, right? Okay, so let's do that with an example. And we're going to have to open a new one. You take the Heineken one. Here it is. You have to return of Heineken, and you have to return of the AEX, which is, of course, an index. And what we are going to do is we are going to test this model where Heineken is the y, which depends on the return of the AEX. If you have the CAPM model, you will probably also know that that depending on the beta term as well, the return of something depends on the market return, which they here take to be the AEX. And how it depends on this depends, of course, on the beta term. If the beta term is very high, then there is high risk. And yeah, it sort of multiplies the AEX. And if your beta is small or even negative, it's the reciprocal. So what we're going to do is first you always estimate your normal model. You go to the Heineken, you go to Analyze, Regression, and Linear. And you put your Heineken in the dependent one and the AEX in your independent one. And you're going to go to Save, and you save your unstandardized residuals. Continue, because we of course want our residuals to test if the residuals are independent. So that makes sense. And then we get our model. But what we want is to test the lag of the residuals. So you go to Transform, and you call it like lag res. That's how I would say. And you type lag between brackets, and you put your residuals in it like this. How do I know this term? Well, we just learned it in a lecture. I think you can look it up somewhere, maybe in arithmetic. Yeah, here it says, for example, the ln, which we used. To be honest, I don't know where it is exactly. Maybe time duration. No, I don't know. It should be somewhere in here, but if you just remember it's lag, I think you can remember that. And you put the res in it. Okay. And here it is. Of course, it's going to leave the first one blank. Why does it leave the first one blank? Because you can take the residual, the lag of the first residual, because there was no day before it. And there's also going to be one, yeah, like this. It doesn't take the following of this, which it also can, of course, not do. So yeah, there's going to be one less. And you also have to take note of that if you are testing, because now, like I said, sometimes there are errors in your data set, and then data are missing. And this can be seen as an error of data missing. It's not really an error because it makes sense that it can't have the first leg, but it's still data missing, which of course influences your degrees of freedom. And that's also why you always have to get your degrees of freedom from the table and not just scroll down. Because if I scroll down, here, you see there are some data missing here. If I scroll down, I would say, oh, it's 510. If I have a model with one variable, and of course your beta 0, oh, then the degrees of freedom will be 508, right? Well, it's not, because here there are two missing. And there's one missing here as well, so it will be lower. Now we're going to make a new model, the model that I suggested for testing I take this out, for testing the residual dependence. And then we wanted to test if the unstandardized residual depended upon the lag, right? That was in our model. This is our model. The unstandardized residual, you want to test if it depends on our lag. And you're going to click OK. Here is our model outputs. We still had the predicted value, etc. on. Where is my coefficient? Here's my coefficient table. So I wanted to do a t-test like this one. And I wanted to test if this variable is significant or not. Here I already see it has a very high significant level. And I can just use my t-value as well because my hinge is 0. Why is it 0 again? Because I want to test just simple significance. So if it's different from 0 or not, so my hinge is then 0. So I put in, if this is my t-statistic and this is my significance level, probably, or this is my p-value, sorry, probably they gave us an alpha. And if we know this alpha, no, they didn't give us an alpha, but probably our alpha won't be like 0.4, right? Our alpha is always 0.1, 0.05, or 0.01. And obviously, even I can see this number is a lot higher than those alpha levels, which means that we do not reject H0. And our H0 was, remember we were doing a hypothesis test of whether H0 is 0 and H1 is non-zero. And here we say we cannot reject H0, which means that the beta, or we call it the weird Y thing, Y1 I call it, is non-statistically different from 0. So we don't know if it's different from 0, so it might be 0. So we don't reject H0. And if we don't reject H0, then if this is 0, then ET doesn't depend on its lag. So it's not dependent upon the previous day, for example, or the 10 days before it. Thus, the residuals are independent in this case. If this weird Y thing was actually different from 0, so we would reject H0 and tentatively accept H1, then we would say that that it depends upon its lag, and then there is dependence between the residuals, and you don't want that because then your standard errors are incorrect. But as we say here, we don't reject H0, and there is no evidence of first order autocorrelation, which means dependence, or first order autocorrelation is just a different word for it. I wrote it down here, I think, yeah. You need to know that word, by the way. Sometimes they ask test for first order autocorrelation. And yeah, correlation, of course, is whether one depends upon the other. So you can make up that it's the error terms depending on the previous error terms. And we say there is no evidence of dependence or first order autocorrelation in the error terms. Are there any questions about any of this or any previous things? Because I think the last theory is at first a bit hard to understand, although the testing, of course, is the same, but you need to know which sort of formulas to use. So the model, and there are a few different models, but they're always the same for the different assumptions. So if you know them, then it's cool, I think. So are there any questions? Like, by the way, if I talk too fast or I'm unclear on something, like I would like to know, because yeah, like I said yesterday, I don't see it on your reactions, so I don't know if you understand. If there are no questions, I suggest we have a break until 10:02. So a bit more than 20 minutes. I think that should be fine. And then we have like 3/4 to start on the exam, practice exam. All right. Yeah, I hope you guys followed along and that you are still there and not that you just are doing something else. Yeah. So anyway, we'll have a break and I hope it's been useful for you.